Right, in this video I'm going to talk about the three inverse trig functions that are most important for us to know: inverse sine, inverse cosine, and inverse tangent. And I'm just going to kind of quickly go through each one and what you need to look for when you're evaluating it, and then just do one example of each one. I'm just going to quickly go through this. So I did other videos where I explained in a lot more detail about each one of those functions, and I did quite a few examples of doing each one. So this one's just kind of putting them all together in one single video, just so you can kind of compare and contrast them to see what you have to do to evaluate each one of these different inverse trig functions. All right, so the first one I have up here is the inverse sine function. Remember, there's two notations we use. The sine with that exponent -1. Remember, that -1 exponent means the inverse. So that's the inverse sine function, or arc sine. Right, that arc in front of the trig function means the inverse of that trig function. Right, so for the sine inverse or the arc sine function, those two, it's the same function, they mean the same thing. We use the right half of the unit circle, right, between -π/2 and then +π/2. Right, so all our answers for the inverse sine function come from the right half of the unit circle, and we look for the y coordinate, right? And the reason we look for the y coordinate is because we are dealing with the sine function. Remember, the definition of the sine function in terms of the unit circle, sine of π/3 or whatever, is the y coordinate of that terminal point. Right? So when I'm doing the inverse sine function, basically what they're giving me is the y coordinate of a terminal point. So I go to the right half of the unit circle, I look for where I have a y coordinate that matches the number that I'm given, and then the pi number is my answer to that inverse sine function. Right, so those are the key things for inverse sine. Right half of the circle, I'm looking for the y coordinate. Right, and the right half of the circle, again, I explained that in the videos that I did on the inverse sine function, how we have to restrict the domain and only look at some of the numbers. So if you don't understand why we're using the right half of the circle here, go back and watch that video I did on just the inverse sine function, where I explained in a lot of detail why we only use half of the numbers on the unit circle. Okay, so inverse sine, right half, look for the y coordinate. I'm looking for a y coordinate of -√3/2, and I'm trying to find arc sine of -√3/2. Remember, arc means the inverse, right? So I'm looking for y equals -√3/2. So I'm going to use my trig hand to try to figure this out. You can do these in a lot of the videos that I did on the doing these examples. I had the whole unit circle up here with all the numbers, but you don't have to have the entire unit circle in front of you to do just a single arc sine or inverse sine problem. And I'll show you how to do that without actually having to fill in a complete unit circle. All right, so arc sine of -√3/2. It's a sine, so I'm looking for the y coordinate to be a -√3/2. So if I go to my trig hand, I want y to be √3/2, so I put down my index finger, right? That gives me an x of 1/2 and a y of √3/2, right? So, and that index finger corresponds to π/3, right? So at π/3, I've got 1/2, √3/2. Right, from my trig hand, I get that. And if you didn't see the video I did on trig hand, check that out so you know what I'm talking about here. But that's my terminal point for π/3. The y coordinate there is +√3/2. I want -√3/2, which means I just need to reflect that point down into the fourth quadrant, where the coordinates will be +1/2, -√3/2. And if this is positive π/3 up here, this point down here is -π/3. So arc sine of -√3/2 is -π/3. Right? I don't have to draw the entire unit circle. I don't have to fill in every single terminal point of every single point on there to do this. I just need to identify, I need a y of √3/2, trig hand, put down this finger, that gives me y. The number of fingers below is your y coordinate. That's √3/2, but that's positive up in the first quadrant. So for the negative, I have to flip that over, and I get -√3/2. Gives me the answer of -π/3. Sorry, I completely forgot what I was saying there. All right, so that is our quick review of the arc sine function. I'm going to pause this and then put up the information for the arc cosine function, and we'll see how that's similar and how it's different from the inverse sine function. All right, here we have the inverse cosine function. So again, two notations, the cosine with the -1, right? That's our notation for the inverse function. That's cosine inverse, or we can call it arc cosine. Right, so two different notations that denote the inverse cosine function. Now for the inverse cosine function, we're only looking at the top half of the unit circle between 0 and pi. Right, so, and again, the reason we do that I explained on the video where I talked about the inverse cosine function, and again it relates to the graph of the cosine function and how we have to kind of split that graph apart to get an inverse function. So if you don't remember why that is, check out that video I did on the inverse cosine function specifically to explain why we only use the top half of the unit circle. But basically what we do then, we look at the top half of the unit circle, and then we're looking for the x-coordinate, right? Because the definition of the cosine function gives me the x-coordinate of the terminal point, right? So when I'm evaluating inverse cosine or arc cosine, I look at the top half of the unit circle, and I look for the x-coordinate that matches whatever number I'm given here, right? So for the inverse sine function that we just talked about a couple minutes ago, inverse sine is the right half of the circle looking for the y-coordinate, right? Inverse cosine is the top half of the circle looking for the x-coordinate, right? And again, it all comes back to the definitions of those functions in terms of the terminal points on the unit circle. It comes back to what the shapes of those graphs look like. So if you're confused about any of that stuff, go back and look at some of the videos I did where I explain all those things, and hopefully it'll start to make sense, right? But it's all these different things put together that determine that for cosine inverse, I do the top half and I choose the x-coordinate. We didn't just randomly decide, okay, for cosine, let's just use the top half of the circle and let's go for the x-coordinate this time. There's a reason why we do all those things. And if you understand those reasons why, it makes it a lot easier to remember what to do when you're evaluating these inverse sine functions. Right? So the definition of cosine is the x-coordinate. That's why when we're doing inverse cosine, we're looking for the x-coordinate. All right? So arc cosine of negative root 3 over 2. All right, so this is going to be the x-coordinate of one of the points on the top half of the unit circle between 0 and pi, and I have to figure out where that point is and what's the pi number that gives me that terminal point with an x-coordinate of negative root 3 over 2. All right, so once again, I'm going to use my trig hand just like I did for the inverse sine function a few minutes ago. I want x in this case to be a negative root 3 over 2. So if I put down my ring finger here, I have 3 fingers above, so my x would be root 3 over 2, my y would be 1/2, and the the ring finger corresponds to pi over 6. All right, that's the first one we have up here above 0. So at pi over 6, my terminal point is, again, if I put down that finger, the root 3 over 2, the number of fingers above is my x-coordinate, so it's root 3 over 2 for the x, and then the number of fingers below is my y-coordinate, which is just 1, so it's 1/2 for the y. All right, so there's my terminal point for pi over 6. Now I want the x, though, to be negative root 3 over 2, which means I reflect this point over into the second quadrant, and there the terminal point is going to be negative root 3 over 2, comma, 1/2, and that's where I have that x-coordinate of negative root 3 over 2. Right? Remember, when you're in the second quadrant, any point in the second quadrant is going to have a negative x-coordinate, but a positive y-coordinate, just because of its location on the coordinate plane. So now the thing is, well, what's my pi number for this point over here? Remember, there are similarities. If you didn't see the video I did about the full unit circle and some of the similarities between the points and the pi numbers on each side and how to figure out how to fill in each quadrant, I would advise you to check that out because it's real important to be able to do that quickly here for one of these problems. So the pi over 6 reflected over into the second quadrant is also going to involve a pi over 6. It's just going to have a different number in the numerator. And in the second quadrant, the general rule is that the numerator number is 1 less than the denominator. Right? So that number over there is going to be 5 pi over 6. Right? Which makes sense, right? Because 5/6 of pi is a little bit less than 1 full pi. So 5/6 pi is a little bit above that, or if I'm going around this way, just before I get to pi is where I go through 5/6 pi. Right? And again, I explained those rules like when I said that the 5 is 1 less than the 6. I did a video where I explained all those rules for working with the unit circle, so make sure you check that out if you don't know how to figure out that that's 5 pi over 6. Because there are some really easy ways, some easy methods to remember all the numbers you need on the unit circle without actually memorizing the whole thing. All right, so that's our arc cosine or inverse cosine function. All right, when I'm given an arc cosine or inverse cosine, I look at the top half of the unit circle, and whatever number they give me, I'm looking for the point on that half of the unit circle that has this x-coordinate. Right, so again, sine is the right half looking for the y, cosine is the top half looking for the x. Right, and those are based on the definitions of the sine and cosine functions. All right, I'm going to pause this one more time and then put up some information about the inverse tangent function, and we'll do a little bit about that as well. All right, so here we have the tangent inverse function, and again, 2 notations just like all the other ones. We have tangent with a -1, that's our tangent inverse notation, or arctan. All right, so those are the 2 notations we use for the same function, the inverse tangent function. All right, so for the inverse tangent function, we're looking at now the right half of the unit circle. right? So the inverse tangent and inverse sine functions are similar in that for both of those we use the right half of the circle. The inverse cosine is the one that's different. That's the one where we use the top half, right? So sine and cosine, or sorry, I just said that wrong. Sine and tangent are the right side. Cosine is the top side of the circle, right? So that's the first major thing when you're evaluating the inverse trig functions is where do I look on the unit circle? Sine and tangent, we look on the right side. Cosine, we look on the top side. And then the other thing we do is, well, what do I look for now that I know which part of the circle to look at? What am I looking for? So for the inverse tangent function, the right half of the circle, we look for y over x. And that, again, goes back to the definition of the tangent function. The tangent function, for whatever number I plug in, that's the distance I travel around the unit circle. And then that terminal point there, the x and y coordinates, the tangent function is the y divided by the x coordinate, right? So tangent function or the inverse tangent is a little bit more difficult to evaluate than the sine and cosine. Because remember, sine, I'm just looking for the y coordinate. Cosine, I'm just looking for the x coordinate. So those numbers are just there on the unit circle. For the inverse tangent, I'm looking for y over x. So I actually have to take the y coordinate and the x coordinate and put them into a fraction and simplify that to see if it's going to give me this number here, in this case, square root of 3 over 3. All right, so here I want to find arctangent of root 3 over 3. So I got to figure out, all right, so which point on the right half of the unit circle, when I take the y coordinate over the x coordinate, is it going to give me root 3 over 3? Well, with that root 3 there, I know it's going to be one of the ones with root 3. Right, so it's not going to be 0, right, which has the terminal point 1, 0. Right, if I do the y over x there, it's not going to give me this. Right, it's not going to be the pi over 4, the one in the middle. Because remember, for pi over 4, the terminal point is root 2 over 2, root 2 over 2. And if I put the same number over itself, it's just going to equal 1. So it's going to be either the pi over 6 number down here or the pi over 3 number up here. It's got to be one of those two because those are the two that involve the square root of 3. All right, so for pi over 6, my terminal point is root 3 over 2, comma 1/2. There's barely enough room to write this here. So root 3 over 2, 1/2. For pi over 3, right, if I use my trig hand for that, it's 1/2, comma root 3 over 2. All right, so it's got to be one of those two, and it's going to be the y over the x. Well, for pi over 3, if I do the y over the x there, it's root 3 over 2 over 1/2. That's going to have the root 3 on top, but then just a 1 on the bottom. That's not going to be this. So I'm pretty sure it's going to be the pi over 6. So if I take my terminal point, root 3 over 2, comma 1/2, right, that's my terminal point for pi over 6, and then I do the y over the x. Right, so y over x is going to equal 1/2 over root 3 over 2. Right, when I do that, the fractions, the halves, cancel, and I get 1 over the square root of 3. Right, well, that's not quite square root of 3 over 3, but if I rationalize the denominator by multiplying both the top and bottom by the square root of 3, I get the square root of 3 over 3, which is what I'm looking for. Right, so arctangent of root 3 over 3 equals pi over 6. Right, because when I do tangent of pi over 6, and I do the y over the x, 1/2 over root 3 over 2, when I simplify that, I get the number that they gave me here, root 3 over 3. Right, so evaluating the inverse tangent function takes a little bit more work than just evaluating inverse sine and inverse cosine, right? Because for tangent, you actually have to create the fraction y over x, and you actually have to simplify to double check to make sure it works. Now, like I mentioned in the video that I did on inverse tangent, there's only so many different possibilities you can get, right? We only have on the right half of the unit circle, we've only got 7 points where we can put the y over the x and get an answer to it. And the 3 from the first quadrant, the 3 in the second quadrant are the same, except they're negatives. So really, there's only 4 different numbers you'll see doing inverse tangent from the unit circle. So once you do a few of these examples, and if you've watched all the videos I've done on the inverse tangent and then this one here, I think we've done almost all of them already. So once you practice a few more, you start to see, oh, root 3 over 3, that's going to be the pi over 6, because I've already done that problem like 2 or 3 times. Right? If it's just square root of 3, that's going to be pi over 3. If it's 1, it's going to be a pi over 4. Right? So you start to get the hang of those as you practice and do more of these types of problems. All right, so that's it for our summary of the inverse trig functions. Again, knowing which half of the circle to look at, and then the x and y coordinates, which one you do. So once again, sine, right half, look for the y. Cosine, top half, look for the x. Tangent, right half, look for y over x. If you remember those 3 things and you know your unit circle, you can do any of these inverse trig functions. It's just a matter of going through the steps and actually going ahead and doing it.